Wycliffe Mogalu. I'm going to be presenting the project titled Interpretable Machine Learning for Predicting the Likelihood and Cause of Customer Churn in Retail Banking. It's a class project that I've been working on together with my partner, Sudi Murinda. The background of the problem is the idea of customer churning, which is a customer's tendency to discontinue engaging with an organization. And research shows that the estimated cost of acquiring a new customer is 6 times more compared to retaining an existing one. So that being said, banks must try to retain their existing customers over trying to acquire new ones. So in the machine learning community, research on customer prediction has yielded some promising results, especially with the ensemble learning methods. So the problem statement states that retail financial institutions strive to retain their clients and draw in new ones. Customer attrition brought on by unfavorable economic or other outcomes affects the economics of these financial institutions. And that being said, it's crucial to determine which customers are likely to churn and comprehend what leads a committed customer to churn in order for that institution to boost its revenue. Some of the research gaps we encountered while reviewing similar and closely related work include the fact that the high scoring models typically did not explain their results, and therefore there is room to explore explainable AI approaches, particularly model agnostic ones like Sharp and Lime. And then work that takes into consideration multiple domains turned out to have skewed performance results, with commonly telecom data having higher accuracies. So one example was a random forest strategy that achieved 77.53% accuracy over insurance data and 95.9% on telecom data, while having approximately 90% for banking data. And then another thing that emerged was that the fact that several resources used accuracy to evaluate their models. However, given the fact that churn data is typically imbalanced, accuracy wouldn't be the most suitable metric to measure or to assess the model's robustness, especially towards the smaller sized class, at least not on its own. So the more meaningful metrics would be area under curve, F1 score, and recall. And then lastly, there's scarcity of real-world banking data. The popular data set from Cargo that most of the approaches used has not been verified or linked to any real-world banking institution. So the objective of our research was to create a unique data set that shows customer behavior, and this was to be generated from the Backer database that we'll look at shortly, and then to establish class labels for Backer features using a deep clustering approach, and then develop multiple machine learning algorithms using both Backer and Cargo datasets, and then explain our model's predictions using model agnostic explainable AI techniques. So the data, the first data source was the Backer database, and this is a real-world database that includes financial and transactional data from an anonymized Czech Republican bank. In the database, we have approximately 1 million transactions from more than 5,300 customers, with records about 700 loans and 900 credit cards. So the data is presented in tables that are represented by the relationship diagram below. So you can also comprehend the relationships between the tables by inspecting the relationship keys in this diagram. Then the other data source was Cargo. So the Cargo community provides a bank customer churn data set, and this data set is already curated for machine learning and it has 13 features. This was a data set that most of the papers we reviewed actually used, and these were the features in that data set. So for our methodology, of course, we begin with the data, and then we go through an exploratory data analysis stage at which we try to understand our data and clean it. So we understand the data by posing hypotheses and trying to understand which features are important, whether or not there is bias towards particular data categories, and then also feature engineering is done at this stage. Then after we have the processed data, we experimented with both clustering and classification approaches. So the clustering, we experimented with both k-means and deep clustering, but the final labels that we generated for the BACA data features was utilizing the deep clustering approach. So once we have labeled data, we run several experiments, including ensemble learning methods, decision trees, and also the k near neighbors, support vector machines, and logistic regression to perform the classification. And then once we had the models that we deemed good enough, in order to acquire top performing models, we used the naive approach, the random search optimization with cross-validation, to tune the hyperparameters of our models. And then evaluation was k-fold, tenfold in this case, cross-validation. And then once we had a model that we deemed good enough, we generated explanations for the model predictions using both Sharp and Lime. So our data pipeline was essentially something like this. We begin with the EDA. With the EDA, we of course establish a hypothesis. For example, something like is this data biased towards a particular gender or a particular location or a particular age? So we establish those hypotheses and try to understand through data wrangling and visualization, and this helped us understand which features are suitable for the classification. And then so this is a visualization of some of the most influential features from the analysis of the deep clustering results. So these were some of the most influential features out of the 35 features that we managed to extract from the data from the BACA database. In terms of our data partitioning, first of all, both data sets were imbalanced. On the left-hand side, I have the BACA dataset, and on the right-hand side, I have the cargo dataset. So with the BACA dataset, we had roughly 3,800 images with the active customers, and then about 1,500 for the churn ones. And then on the other hand, for cargo, we had approximately 8,000 images for the active class, and approximately 2,000 for those that churned. So in terms of partitioning our data, we took 30% of the data and separated it for the test case, and then 70% for training. For validation, we applied a tenfold method, of course, on the training partition, with the training partition. So these were the results for our classification on the BACA dataset, and as you can see, it was pretty good, but the random forest algorithm outperformed all the rest with all metrics. And again, with the cargo dataset, the overall performance was generally low, and this goes back to the nature of the dataset and the limited number of features. Yeah, but the random forest still outperformed the rest. So we went ahead to explain the results of our models using Lime to begin with. So what Lime essentially does is it approximates the model, the underlying model, or the model that we developed by creating an interpretable model, and this is created by taking into considerations the local data point and its surroundings. And then with that interpretable model, it's able to generate explanations of how of how the features affect the predictions. So in this case, so this is what the explanation looks like from Lime, and part of the explanation we have the predicted probabilities for both classes, and we can see the predicted probability is higher for the class 1, which is the churn class. And then in the middle we have a decision sort of boundary from which Lime bases. So at the boundaries we have threshold values associated with our weights for every feature. So basing on whether or not a given feature exceeds the threshold value at the boundary, it contributes towards a particular class. So on the right hand side we have the actual weights for each feature, and these are the weights that are generated by the interpretable model. So just for better intuition, let's take for example the transaction count. You see that the value is 1.24, and then at the decision boundary, the rule is that if the value at the decision boundary is 1.04, so that means that if the transaction count is exceeding 1.04, then it contributes towards the positive class. Otherwise, it contributes towards a negative class. So in this case, it was 1.24, which is exceeding 1.04 by 0.2, and for that reason, it becomes the most influential feature for predicting that this data point in particular belongs to the positive class. And then the other explanations we generate are sharp explanations, which essentially creates sharp values for every feature, and the sharp value is essentially the average of the expected the average of the contribution of the feature. So the bigger the sharp value, then the greater impact that that feature has towards the prediction. So you see that the transaction count again has a much bigger sharp value, and so depending on the sharply value, it has the most influential impact on deciding what class the given data point belongs to. So in conclusion, churn prediction still remains an important phenomena to look into, especially in the financial domain. And we conducted several experiments for classification, and we found out that ensemble learning approaches outperformed other classification methods, and particularly the random forest emerged as the best on all occasions for both data sets. We used explainable AI. We used model agnostic approaches, including Sharp and Lime, to explain the predictions of our model. And then in terms of one of the challenges and concerns is the fact that the Baka database was developed in the late 1990s, and that being said, it probably lacks on some attributes associated with modern banking processes. So for future work, we plan to demonstrate the impact of using deep clustering to generate labels given a labeled dataset. So that means we use the deep clustering to generate the labels, and then we assess the reliability of the generated labels. So still I'd like to extend my appreciation to Mr. Galiwango Marvin, a lecturer at the Department of Computer Science, Macquarie University, whose advice and technical insights have enabled us to come up with technical contributions for this work. Thank you.